Hi folks, Mr. Long here. What I'm going to do now is formalize the first part of the fundamental theorem of calculus with proper calculus notation. Okay, so we're going to use the same graph so that you understand it. What I need to do is to define some functions. So f of t is going to be our small f of t is going to be our rate function. Big F of t is an original function. Now, a good question is that people have had as we've worked through some of the stuff is this the accumulation function? Actually, it's not. This actually tells you how deep the snow is. It doesn't say how much is accumulated. So when I have a rate function, but I also have, for example, an initial value of depth, then I can get the overall original function. You're going to see as we work through it. Okay, so centimeters per hour is clearly rate. So this graph that we're given is a rate function. Okay, we call it small f. Okay, so let's look at what these functions look like. So the original function, well, first of all, the rate is what we're given. Let's go to that. So the rate is in centimeters per hour. We know it's a rate. It was given in the question. It's right on the axes. That tells me it's a rate. So I try to, when I can, label rates as small f, or small letters, right? And then hours on the x-axis. Now, the question is, how do I get centimeters per hour with hours there and turn it into centimeters? Well, clearly I've got to take centimeters per hour and multiply by hours. And then the hours would cancel out, and I'd be left with centimeters. So that means to go from a rate to an original graph requires area. Okay, it does require a little bit more than that. Area just gives me the accumulation, but nonetheless. And then what about going in the other direction? What if I took the slope of this graph, delta y over delta x? Well, the units on delta y would be centimeters. The units on delta x would be hours, centimeters per hour. So if I take a rate of an original, I get, or if I take the slope of an original, I get the rate function. Okay, the rate function. Okay, so let's start figuring out what all these things are. Okay, so what is this 40 centimeters given our notation? So first of all, centimeters. Does centimeters go on the original or the rate graph? Well, obviously, 40 centimeters goes on the original, and that's at 10 a.m. 10 a.m. is t equals 2. That's t equals 0, and 1 p.m. is t equals 5. Okay, so that 40 centimeters then, what does that represent? That represents big F at 2 hours equals 40 centimeters. That's a depth, right? That's the original function. That's not rate. Okay, so we know that. So that's what we know. Then we want to figure out, what we want to figure out is the depth at 8 a.m. Depth. Is the depth of snow big F or little f? Well, we think it's big F because it's an original. So I want to figure out what f at 0 is. That's my unknown. Okay, my unknown. So if I go down to here and start writing some notation, so this is what I want to figure out. And I know that it was 40 centimeters deep at t equals 2. Then I'm going to accumulate a certain amount of snow. Okay, but this is a weird, remember this is the weird one. I have to go back in time from 2 hours to 0 hours. So is there going to be less snow or more snow? And with this case, we went through this, and delta y was 3, delta x is -2 because we're back in time. Okay. So what I'm going to do right now is put it into the notation. Well, first of all, we'll get the answer, right? So we know that that's our final answer. F at 0 is 34. We got the same result in the previous video by not using any calculus really at all, just intuition. So what we need to start doing, though, is start developing some calculus-based notation for this. So for this one here, so this is what I'm trying to figure out right here, f at 0. And then what I'm doing is I'm taking f at a, okay, or sorry, f at 2, which is the known value of 40. And then I've got this symbol, this integral symbol, which means add up all the area between two x values. Okay, and the first x value is, I'm going from 2 hours to 0 hours, right? Because I'm going backwards in time. So one of the things that you need to know when you see this symbol, that the bottom one is where you start, that's from, and this top one is 2, that's where you're going. So you're going from 2 hours to 0 hours, okay? And then we call the function f of t dt, because this right here, f of t, that's like our delta y, right? Because f at x is a y value. dt is what we see on the x-axis, right? Delta x. So delta y multiplied by delta x. Okay, so some things to think about. By the way, we call this value down here is called a. This value up here is called b. And we call these the limits of integration, okay? The limits of integration. So I will, over here, I'm just going to put, if I have an integral from 0 to 5 of f at t dt, what that means is I'm getting the area under the f at t curve from an x value of x equals 0 to an x value of x equals 5. And I'm going to multiply together the y values and the x values to get the total area, okay? There's your y values, there's your x values. So I go ahead and, so again, what we do is we label these. So the thing that you want to figure out in this case is you want to figure out big F at an x value of b, knowing big F at an x value of a, and then add on all the accumulation, okay? So how do we get this? How do we do this? Well, I'll just write it right there. Okay, so f at b represents the unknown y value we want to figure out. F at a represents a y value on the original that we know, okay, that we know. And then right here, this is the area or the accumulation under the rate graph, okay, from x equals a to x equals b. Okay, and that's what, so if you look at this, actually, we're getting a rate graph out of this, okay? We're taking a rate graph and we're getting an original function from that, okay? So what I'm going to do now is just do it on the other side. Okay, so this is the case where we wanted to get, you know, what was the depth of snow at 5, t equals 5, knowing t equals 2, the depth was 40. Okay, so the thing that you know, we call f at a. Okay, the thing that we know, we call f at a, big F at a. And that's what we want to know. Or sorry, that's what we do know. What we want to know is the depth at 1 p.m. Okay, the depth at 1 p.m. And that's called f at b. And that's why the equation is set equal to f at b, because it isolates the unknown for us. And then I have to figure out all the snow that's accumulated between x equals a and x equals b. Okay, so here we go. Here is our formula. This is the fundamental theorem of calculus right here. Whoops. It's where we connect areas and rates and original functions through area. Okay, through area. Okay, so I want this, I'm given this always, and this I need to be able to calculate. What did they give me? They gave me big F at 2, 40 centimeters deep. They also, I need to know that I want to figure out the depth of the snow after 5 hours, big F at 5, which means I have to accumulate the snow from 2 to 5, right? So notice if there's a 2 here, there's a 2 here. If there's a 5 here, there's a 5 here, okay? So when I go to calculate this, then I have 40 centimeters for F at 2, and then I have to do F at t, which is 3 centimeters per hour, multiplied by dt, which is really delta t, right, or delta x, So this here we changed by 3 hours, and it went to the right, so that's a positive. Okay, so then it becomes 40 plus 9 is 49 centimeters, and that's F at 5. Okay. So just as an aside too, sometimes you're going to see, so sometimes you won't see F at B by itself, for example, right? You're going to see these two being subtracted from each other. And that's where we're dealing just with accumulation, okay, just with accumulation. So this represents the area under the graph f at x between x equals a and x equals b. But what does that turn into? This is the accumulation, right? So this, for example, from the second thing, we got 9 centimeters. That was our accumulation, right? So what that means is that's what the y value changed by over those 3 hours. Okay, the y value increased by 9 centimeters. So think of this as delta f of x, right? From x equals a to b. That's what this is. Okay, it's how much the y value changes by. F at b minus f at a. Okay, it's the amount of change in y value. So area under the curve is equivalent to the change in y value of the original. Area under the rate graph is change in y value of the original. And this fundamental theorem that connects these ideas. Okay, folks, so I'm going to stop this video here. Again, pause, rewind, go back over, make sure you understand it. Look at the Jamboard that's available for you, and certainly ask questions as needed.